Hello, everyone. After defining the water potential in the previous lectures, now we are ready to tackle the so-called soil-plant-atmosphere continuum. We'll introduce it briefly now, and then we'll start with the first component of this continuum, the soil. We'll deal with soil classification, we'll see the definition of the main variables, making sure that we understand that those are valid at the Darcy scale. We'll explain what that means. And then we will focus on soil hydraulic properties, how water moves through unsaturated soil, and describe the equation for the soil-water balance. This will be the starting point then for our stochastic description in part 2 of the course, reminding ourselves that this implies vertically averaging the equation of soil moisture through the soil layer, the root zone, or the active soil layer. The Soil-Plant-Atmosphere Continuum, or SPAC, is this continuum between the soil, plant, and the atmosphere, implying that there is a continuum of water potential, of therefore Gibbs free energy, going down from the soil into the atmosphere, where the direction of the water flow is in conditions of no rain. Water is in the soil, gets uptaken by the roots into the plant, gets into the branches. At the leaf level, there is evaporation, and the water exits by diffusion through the stomata, and then turbulent flow takes it into outside the canopy into the logarithmic layer. The fact here is that we can describe this with the main variable being this psi here, which is this water potential, higher in the soil, lower in the plant, in the leaf, and then in the atmosphere. So we'll study that flow. We'll begin with the first component, the soil. Broadly speaking, the soil is a composite mixture of air, water, and mineral. This is, of course, a huge simplification, because in reality, soil is a very complicated biomaterial with living components, microbes, bacteria, fungi, organic matter, very complicated chemistry, and so on. But to begin with, let's just assume that the soil is made with air, water around it, and grains, aggregates that are just the solid component. So if we take a representative volume, we can say that there is a fraction of it that is air, part of it that is water. These two together comprise the pore space. The pore space could be all filled with water, in which case the soil is saturated. Otherwise, the soil is perfectly dry when there is no water and only air. And the rest is the solid mineral component that for us would be simply inert and not deformable. So we can say then that the soil is the volume of the soil is the volume of the air plus the volume of water plus the volume of the mineral, which allows us to define one of the most important quantities for us, the porosity, the fraction of the volume of voids, meaning volume of air plus volume of water, this part here, versus the total volume. That gives us the fraction of pore space available to water. The volumetric water content, which is the volume of water over the volume of soil, which is called also theta, and the relative soil moisture S, the normalized version of that gives us the water content. So is theta divided by N, the volumetric water divided by the porosity. Relative soil moisture, therefore, is 0 when the soil is perfectly dry and 1 when the soil is saturated. It's important to keep in mind that these definitions are valid at the so-called Darcy scale, which is a volume large enough, the so-called representative volume, over which we average spatially the characteristics, the pores, the grains, and so on. It's typically a sphere or whatever blob of volume you want to consider, that it's 5 to 10 centimeters in diameter or something like that. And this allows us to apply the continuum hypothesis. After averaging in space at every point, each with this around this volume, each point can be given a value of porosity, of soil volumetric content, and so on. It's important to keep in mind also that the dusty scale can be pretty big, especially if the soil is coarse textured, and it can be almost of the same order as the rooting depth in some cases, which may or may not be a problem. We just have to keep it in mind when we will consider vertically averaged values. Soil moisture, the relative soil moisture S, is probably our most important variables. We will write equations for it, especially in the stochastic probabilistic part of the course. Soil moisture is a variable that fluctuates in time and in space, especially in time, and it's 0 when the soil is perfectly dry, and it's 1 when the soil is fully saturated, okay? In reality, a perfectly dry soil doesn't exist. Soil cannot be completely dried, taking away all the water molecules from it. But it can be in equilibrium with a very dry condition, an oven or an atmosphere during the drought that is very dry. The residual value of water that remains in the soil is called the hygroscopic, defines the hygroscopic point, and is the residual value. It's a small quantity in general for typical soils. It can be 0.08 for sands, but it can be relatively high if you have a fine texture soil like a clay. You can have in dry conditions soil with still almost 40% of water if you have pure clay. The water is now, of course, held very tightly inside the pore spaces and cannot really be taken away easily by plants or even by evaporation. The porosity is the ratio of voids versus total volume of soil. So if we say that the porosity is 0.4, it means that 40% of the space in the soil is voids. Somewhat counterintuitively, it's higher for clays that are fine texture than for sand. This is not only because of how the particles are arranged, but also for their shape. The soil is in reality not very homogeneous, especially both in horizontally and vertically. Vertically, especially, it's often characterized by sharp transitions between the so-called horizons, which are the typical layers of the soil. So we have an O horizon, which is the organic horizon, that if the soil is heavily vegetated, it could be relatively thick, like in a forest. And then there is the A horizon, where most of the roots are. This is the finer part of the soil. There is lots of organic matter and most of the roots, as I said. Then there is the B horizon. The B horizon is soil that is coarser, very few roots now, little life, not many microbes, not much carbon, and typically is where the clays accumulate. Therefore, there will be relatively large amounts of silicates, iron, aluminum oxides, calcium carbonates, and other substances percolating from the surface. Below that, the C horizon, we are in the presence of a soil profile that has not been weathered much, the still big rocks coming from the underlying parent material. This part altogether is also called the regolith, and there are, as I said, big rock intrusions and less abundant plant roots and microorganisms. And below, then from this point below, we call it the bedrock, which can of course be fractured, and the transition may not be necessarily that sharp as here. There are different types of soils, and there are many classifications for it. This is a classification based on soil orders. The main soil orders are listed here. There are 12. There are many more in the literature, but these are the main ones, starting from young soils to older soils. And in parentheses, you have the fraction of the surface of the land on Earth that is mostly made up with this type of soils. You can read the description; it's very interesting. It's mostly qualitative, but it gives you an idea of the richness of this. Now, of course, the soil evolution, the evolution of this type of soil from empty soils to oxysoil depends on age, time, and we're talking about hundreds of thousands of years, if not millions in some cases, but also, of course, on climatic conditions and vegetation conditions that can accelerate the transition from one soil order to the other. What is really important for us is how water behaves, moves, or its energetic properties inside the soil. And we are talking about especially unsaturated soil, where soil moisture is not necessarily 1, but it's somewhere between 0 and 1. We have in mind two types of curves, especially. The first one is the soil water retention curve, which is the curve that links the metric potential psi, which we defined before, is the normalized Gibbs free energy of water, is the water potential component related to the capillary forces, to the interfaces that in unsaturated soil are many, with the volumetric moisture content, how much water there is in the soil. It could be the volumetric moisture content or the relative soil moisture, S. Remember that the two, with no offense, if I remind you of that, theta, the volumetric moisture, is just the porosity times the relative soil moisture. The other important curve that we have is the unsaturated soil hydraulic conductivity. Is how fast or how easily the water moves throughout a soil, and this is meters per second, so it's a speed, and it's a function again of either the volumetric water content or the relative soil moisture. This is both of them, as we will see, are highly nonlinear function of the amount of water that we have. So let's begin with the soil water retention curve. Let's look at its shape and how it is. So it's a function, it's a curve representing the function of metric potential versus relative soil moisture. Here we have lots of water in the soil, 0.7, 0.8, 1 here, so saturated soils, and this is drier and drier soils. So let's take a typical soil, a loam or a loamy sand. This is a coarser soil, this is a finer soil. We will define them in a moment. And what we see is that if the soil water content is reduced, then the metric potential goes down. This is plotted with a minus sign in front. You can see that there is minus here, and it's in a logarithmic scale. So it drops really, really, really fast. And as the soil gets drier, the metric potential gets more and more negative. This is somewhat similar to what happened in the atmosphere with the water vapor. As the water vapor, the atmosphere became drier, the water potential became lower and lower. The typical way in which this happens in soil is through a very nonlinear function of the type, like here, of a power law, where we have a constant that depends on the type of soil, and then a negative power here, minus b, would be a very large number. So this is actually shoots up very fast. Remember that this is in logarithmic scale. And then it depends, through these two constants that depend on the type of soil, it depends on the soil texture. Loamy sand, loam, and so on. We will see how these parameters change as a function of type of soil. Why is this curve important? Because it basically tells us, given how much water we have in the soil, what is its energetic level. Okay, so let's take here a loam. This is S star. Let's say that this is the point in the soil at which roots start feeling the stress and have hard time extracting water from the soil. We will see that that also corresponds to the closure of the stomata at the leaf level. But let's say that this happens at this level, at this energetic level. So when the water potential drops below this value, and we want to know at what value of moisture content this corresponds. Now, if you have a loamy sand, this will be 0.3, and if we have a loam, this will be a much higher value. It's a finer texture soil. The capillary forces are different. The water is held more tightly, and so you can actually contain more water at that level. The same thing here. This is the S wilting point for loamy sand and for loam. It's different, and you can see here that you get starting from a similar value. The plant has a characteristic value, let's say, of suction that can extract, below which then it starts wilting. Well, again, the volumetric water content at which this corresponds is different in a loamy sand and a loam. Similarly here, the hygroscopic point, let's say that the atmosphere is in equilibrium with the soil at minus 10 megapascal. These 10 megapascal are 10%, less than 10% saturation for loamy sand and almost 20% saturation for loam, depending exactly on how the capillary forces change because of the texture. If we want to parameterize these curves, we can use this table. It's in the notes, and you can see that what I was telling you, the number B, the exponent, it can be pretty high. For clays, it's actually 11% almost. Sorry, it's 11.4. The psi s is a value in kilopascal, which changes depending whether you have a sand, a loamy sand, a sandy loam, a loam, or a clay. And these are other parameters we will see later on. This is hygroscopic point, wilting point, the point of onset of water stress that we will see later on. This is the porosity, as I told you. Typical value is 0.4. Remember this as a ballpark figure, but slight variability with soil textures, smaller with sand, higher with clays. Typically, the water retention curve is an empirical curve. It's measured from soils by applying different suctions and measuring the corresponding volumetric water content. Now, by doing that, it means that we are practically averaging over a volume of soil. Again, we are introducing the so-called representative volume and the Darcy scale. This allows us to have a continuum representation at every point in space with a link between average energetic content and water and volume of water available. In practice, what we are doing is we are assuming that there is a local thermodynamic equilibrium over this volume over which we are integrating between vapor, liquid, and solid, everything in thermodynamic equilibrium, as we have done in defining the extended water potential, the metric potential. In reality, we know that things are changing, okay? The soil is drying, the soil is filling up with water when it rains, but we are assuming that this happens at a scale that is slower with respect to the times of equilibration, of thermodynamic equilibration between the three phases. It's not always true, but almost always true, and for us, it will not be in general a problem, okay? There is a set of experiments that I will upload separately that actually shows that at the small scale, when the soil dry or when it wets also, but this is drying soils, the processes are actually very dynamic. It's not in thermodynamic equilibrium. These are courtesy of my good friend Thomas Hückel from Duke University. In reality, however, as I said, we will neglect all of these dynamic component in the soil and assume local thermodynamic equilibrium, step by step, a quasi-static sequence of processes. Let me emphasize once more that what we are doing is assigning values at a point, but really averaging around a control volume that contains many grains that allow us to do a statistical description. This is the Darcy scale averaging of soil physics, of soil hydraulics. This is quite similar not much at the same scale, much larger scale, but to what we do when we define a continuum mechanics in fluids, in doing a thermodynamic limit. Okay, instead of a statistical description for each molecule, we take an average and we just describe their average values. This is how we define pressure, how we define temperature, how we define all the thermodynamic quantities. The soil water retention curve, like as all the other hydraulic properties, have a strong dependence on soil texture. I've shown you already the two curves depending on whether you had a loam or a sandy loam. And but I didn't define what these are. So let's see. There is a classification of types of soil based on their texture. We speak of sand when particles have size between 2 and 0.05 millimeters. Gravel has even bigger particles. Silt has particles that are between 0.05 and 0.05 millimeters, and clays are even of smaller size. When we speak of loam, we have a mixture of sand, silt, and clay, more or less in equal proportion. Some real soils are always a mixture of these types. It's hard to find a pure sand or pure silt or pure clay. To characterize these mixtures, the USDA, the US Department of Agriculture, has proposed an interesting soil texture triangle that is worth seeing together here. It's a equilateral triangle where on each of the sides there is the percentage of sand, clay, silt, and clay. Here, the way you read it is entering in the direction of the arrows. For example, when I speak of loam here in the almost in the center, in the lower part, it means that we have here 20% of loam exactly in this point, 40% of sand, and 40% of silt. That's really the heart here in the center of the loam, and the same way for all the other soil types based on texture. The clay are worth a particular mention because the size of their particles is so small and their composition is such that they tend to behave as colloids. Meaning that they have active chemical properties and they often display a plastic behavior. This is due to their structure, which is irregular, only partly crystalline, consisting of arrangements of silicon and aluminum sheets. It's this sheet structure, which is called clay platelets, that may be also disrupted by the presence of organic matter and especially by water, such that clays can shrink or swell as the water is added or subtracted, making the soil a much more dynamic component. Chemically, they're also very interesting because clays tend to absorb cations like calcium and sodium and organic matter and interact with it. So when we average over the Darcy's scale for a representative portion of the soil and we give average values, it is clear that average is only one quantity, but that there are statistical distributions behind those, especially of grains of different sizes and pores of different sizes. Okay, so it is common to represent grains and pores as using a characteristic size. We can say that the pore has a typical, or the grain has a typical radius, because we imagine it to be of a spherical shape or a tube if it is a pore. This will capture the main characteristics of this single pore or the single grain. In reality, of course, we have aggregates, we have networks, but this is beyond our scope here. But the fact is that we can have in mind this distribution, the statistical distribution of pore sizes or grain sizes. And we call the pore size distribution a PSD here, okay? We can actually link the pore size distribution to the hydraulic behavior. I've already mentioned these sections. Have a read and see for yourself. Many times we can actually approximate this distribution as power law functions, which reflect basically the behavior of the soil as a fractal as a medium with fractal geometry. Fractals typically have a scaling laws, which are of course power laws, and that's what gives rise to a representation of the retention curve and this unsaturated hydraulic curve as power laws, as we have seen. The second quantity that we want to introduce is the soil hydraulic conductivity. We will start with the definition of the soil hydraulic conductivity in saturated conditions for this porous medium here, saturated with water, and we will follow the classic Darcy's experiment that we all know from hydraulics. This filter is as water flow through it in steady state because the levels are kept constant, and the flow is driven by this gradient in hydraulic head between the upstream and the downstream level H1 and H2. Okay, the discharge is proportional, of course, to the cross-sectional area, and the experiment shows that it's proportional to the gradient in hydraulic head H1 minus H2 divided by L, and this is through a proportionality constant that depends on the type of soil that we call Ksat, the saturated hydraulic conductivity. It's larger for sandy soils, it's smaller for clay soil because the particle gets finer and finer, and there is more resistance to this flow. The flow of water through the pore spaces is typically a creeping flow, very low Reynolds number. So this is our classic Darcy's result. To bring it to a usable form for us that we want to express it in terms of soil water potential. Now, this we know from the hydraulic head is the hydrostatic head, so it's elevation plus pressure potential, but it's expressed in terms of lengths. And length for us is nothing but energy divided per unit weight. If we multiply it by the specific weight of water, gamma W, then what we obtain here is actually a pressure, which is the water potential, is energy per unit volume. So by multiplying it by gamma W, we can rewrite this as the gradient d over dx. X is this direction. The gradient is because the water potential drops linearly of psi s sat, meaning the hydraulic the water potential of the soil in saturated condition. Okay, so this is Darcy's experiment expressed in terms of soil water potential in saturated condition. Now, what happens if now the soil here is not all saturated, but for example, only the small pores are filled with water, meaning that the soil moisture is not 1, but is a value less than 1? Well, to get an expression, we resort to what Buckingham did at the beginning of the 20th century. Buckingham is the same of the Buckingham-Pi theorem that extended the Darcy's law to unsaturated soil. So he basically said, look, if let's consider the same type of behavior, but now this Ksat, this function, is no longer a constant, but strongly dependent, strongly non-linearly depends on the degree of saturation. So for a vertical flow, let's say that Z is now a variable that points upward, the flux, meaning the discharge divided by area, so Q divided by A, is now a K function of S. This is the unsaturated hydraulic conductivity times the gradient, like before, of the soil water potential, psi S, still divided by gamma W to get here a length over a length and get something that is just length over time, like this guy. but now the soil water potential is the unsaturated soil, so it contains the metric potential that changes with soil moisture. So if we expand what we have inside here, we have the gravitational component of the soil water potential, and we have the metric potential, so which is nothing but the retention curve, metric potential as a function of soil moisture. This has already been divided by gamma W, that's why you have only Z here. This is the gravitational potential. In front of this, of course, there is the unsaturated hydraulic conductivity. So the flux, according to Buckingham, in unsaturated soils is the unsaturated hydraulic conductivity times the gradient of the soil water potential, the matrix plus the gravitational. If the effects of gravity dominate over the ones related to the matrix potential, then the deep psi S over dz is 0, and we have dz, which is 1, if you look at the previous expression carefully. And so what you will see that the vertical water flux, if gravity dominates, then it's simply Ks. And this is what we call gravity-driven percolation, right? We'll give it a special name, LS, which will appear later on in the soil water balance equation. It's a decent approximation for us later on when we'll do the stochastic analysis. What is the functional behavior? What is the shape of this Ks function? Again, like in the retention curve, and even more so here, it's a very nonlinear function of soil moisture. Sometimes, often I would say, it's approximated as a power law function. We will use that. And the shape, therefore, of Ks is K sat, K at saturation. This is the saturated hydraulic conductivity, times the relative soil moisture raised to a power C. Now, this power C has been empirically or semi-empirically related to the exponent B of the retention curve. There is a short explanation of how this comes about in the notes that I gave you, which I suggest you to read. But the bottom line is that if B was already a relatively large number, remember between 4 and 11, C now it's an even bigger one. So it's 2B times 3. And there is nothing sacred about this power law. It's convenient. It may be suggested by the fact that the soil may be described as a fractal, which has typically a scaling law in terms of a power law of function. But in case you need a different form, this is also a useful one in terms of an exponential, still a very strongly nonlinear function increasing as a function of S. This is a function that increases rapidly with soil moisture. I'll show you in the next slide here. So the shape is this one. We have Ks as a function of S. So for low soil moisture, there is almost no conductivity. And then at some point, still start moving, and then they really increase fast to the saturated hydraulic conductivity. Okay, when you are saturated here at S equal to 1. If you want to do a simple experiment, take a sponge, which is a porous medium, put it under the faucet, and open the faucet, and you will see that at the beginning the water is there, held by the sponge, and only after you reach a certain value of saturation, the sponge starts percolating, and then the percolation gets faster and faster as you increase the discharge from the faucet. So there is this almost like a threshold at which the unsaturated hydraulic conductivity becomes non-negligible. This is an important quantity, important level of soil moisture that is called the field capacity, S sub Fc. It's very much used in soil physics, in agronomy, and we will use it a lot when we need a threshold to define the beginning of percolation. We have percolation to deeper layers when soil moisture is larger than this, and then we can say that practically nothing happens below this point. Okay. Again, this type of curve refers to the behavior of a portion of a porous medium. So it implies a spatial averaging over the Darcy scale, like the previous curve, which was the retention curve. Okay. If you want to see a conceptual model for this behavior linked to the flow of water in capillary tube in these pore sizes of in the pore spaces of the soil as a laminar flow, read the section 3.2.5 of the So in the introduction, we talked about how the biotic component of the ecohydrological processes impacts hydrology. And these are some examples. Here is how organic matter and plants affect some of the hydraulic properties. The first figure here is hydraulic conductivity on the y-axis and relative soil moisture. So we see the strong linearity that I showed you before. And this is an experiment with two different soils. One with a loamy soil with one just as it is and one adding crop residues. And you can see that the hydraulic conductivity increases as you add organic matter, probably because of more spore space is changing the structure. So this is a neat example of how biology, the biological part, the ecological part of ecohydrology affects the water cycle, the soil hydraulic properties. This is another example of how the pore size distribution changes as we add organic matter, in case of the sand and in case of clay. It's plotted here, the pore size distribution in log-law scale, so it becomes a straight line as because of the two logs that you do from if you start from a model that is a power law. And what happens with the sand is that if you add organic matter, you tend to form smaller aggregates here that reduce, relatively speaking, the number of small pores compared to the large pores. You get a kind of a clogging of the smaller pores, so that the pore size distribution from something like this becomes something like that, assuming that it remains a power law. So in all, what happens is that the sand starts behaving more like silt, has a higher abundance of smaller pores. Just the same, but starting from a different point, starting point, it happens for clays, where the original structure here with these disorganized platelets now becomes aggregated by organic matter into bigger aggregates, into bigger structures. So that this gives rise to a relatively greater abundance from here to here. You have a greater abundance of smaller pore compared to the very tiny pores that you had before. So again, clay tends to become now as a silt or something that has at least a higher proportion of bigger pores. And this basically tells us that adding organic matter, if you either have a sand or clay, is good. It's good to have this intermediate type of behavior that is silt. And agronomists and farmers know that very well. Adding organic matter to your soil can only do good in terms of hydraulic properties and then how plants behave in it and grow in it. The last example here is the role of vegetation on bulk density and the saturated hydraulic conductivity. And we can see that this is an experiment done in California, so I didn't put here the references. You can see them in the notes. But the experiment has three different types of vegetation: oak, pine, and this chemise, that is, I don't know how to pronounce it. It's a shrub. And you can see that depending on the type of roots and the rooting depth, the bulk density changes, and you have much smaller bulk density with the oak than you would have with the shrubs or with the pines. And the difference is not trivial. With the pine is almost unchanged as you go down. The typical bulk density of a soil is 1.6 if you have to remember a number. So 1.6 ton per cubic meter, that's the weight, or that's the mass of the soil. But it goes down to almost 1.25, at least at the surface in the first 10 centimeters, 5-10 centimeters, if you have a consistent vegetation, in this case oak forest. The same happens for the saturated hydraulic conductivity, that actually gets much larger than the typical value of a compacted deeper soil here, of also even an order of magnitude. In this case, this is the pine case. So the pine case, although it doesn't change much the bulk density, it really changes the hydraulic conductivity. It probably creates more of the structure of the macropores that you need to percolate water into the deeper layer. So that's interesting feedback of the abiotic component on the physical properties of the soil. So having defined all the soil properties that are important for us and the hydraulic properties through the retention curves and the unsaturated hydraulic conductivity, we are ready to put together the soil moisture equations at the point. I will go a little bit fast here, assuming that you have seen this already in basic hydrology in soil physics. If not, the section 3.3 goes in detail, and you can have a look at these notes later on. But what do I mean by a point here? The point is the point of a continuum after having done, of course, a Darcy averaging type of operation. So when we say here is a point, we mean that this is representative of what goes around it in this 10, 15, 20 centimeters, whatever the Darcy scale is for that type of soil. So the first thing to do is to consider an infinitesimal control volume, as often in fluid mechanics. The control volume is partly saturated, so there is a volumetric water content theta, which is representative of this level Z. We will just do a vertical. We'll assume that nothing changes in the X and Y direction, and so we'll consider a one-dimensional equation in the Z direction. We will have a flux phi at level Z and a flux phi at level Z plus dZ, which are different. And then there is a sigma here, which is a sink term. Imagine that there are roots here of plants that actually suck the water away, and as if they were, it's not, we don't think that they're part of the soil, so we consider them as a sink term. Whereas the percolating or going upward, if you have a capillary rise type of flux in the soil, is a true flux, is a transport term. So let's write the balance equation here related to this picture. We have the amount of moisture in the soil changes in amount of moisture. So d theta times the volume of the little control volume that we have must be equal to inputs minus outputs. And the input is what comes from the flux at level Z times the side times the area of this face here, dy dx, in a time dt. And what goes minus what goes away from the other face of the cube at Z plus dz, where the flux is different. The phase, of course, is the same, dx dy in time dt, minus how much is uptaken by this. It is lost because of this sink term. So this is the sink per unit time per unit volume. So we need to multiply it by the volume, dx dy dz, times the dt, which is the infinitesimal time in which this loss takes place. Okay. The next step, as usual, is to relate these two by expanding this one in Taylor series, which is done here. And so we have this guy that is expanding as the flux in Z plus the correction due to the partial derivative of phi with respect to Z times dZ. This allows us to simplify in the next step. The flux phi and phi here go away because of this minus sign. And just keep then this guy, and this guy. Once we notice that we can divide by the volume, dx dy dz, and divide everything by the infinitesimal time, we get the continuity equation in this form. The rate of change in time, the partial derivative of soil moisture, the volumetric water content in time, is equal to the gradient in Z of the flux with a minus sign in front, minus how much we take away because of the sink term. This sink term is due to the plant. This is typically a percolation through the control volume, or as I said, if it is going upward, some sort of capillary rise. If we combine the continuity equation that we just derived with the unsaturated hydraulic conductivity, the Buckingham extension of Darcy's equation, then it's not difficult to show that with that flux you get an equation in theta of this type, which is the famous Richards equation. The rate of change of theta in T has one term that contains the unsaturated hydraulic conductivity. This is an advection term. It's a nonlinear function of theta, so it's nonlinear advection, and a nonlinear diffusion term here. You see that there is diffusion because it's a second, there are two derivatives here, and this is the so-called soil diffusivity. The soil diffusivity, when you do the operation of combining the continuity equation and the equation of motion, the extended Darcy's law, you will see that it provides this type of soil diffusivity, a strongly nonlinear function of the volumetric water content that contains both the unsaturated hydraulic conductivity and this here, which is the retention curve, how the metric potential changes as a function of theta. So do this exercise and get this form once for all. So, and at the end, of course, we also have the sink term that remains because of the root uptake. So advection, nonlinear advection, nonlinear diffusion, because theta is not a constant, is function of, sorry, D is not a constant, but is function of theta. It's a strongly nonlinear function of theta. And the sink. That's Richards equation, including the plant uptake. Again, have a look at the section 3.3 of the note if you're not familiar with Richards equation. And remember, what are the assumptions behind it? Mostly the averaging over a volume of soil. So it is, yes, a continuum description. It's a partial differential equation defined continuously in time and in space, but it comes having averaged over the Darcy scale with the limitation that may imply. So how do we go from the Richards equation to the soil water balance equation that, as I said at the beginning in the introduction, it is really our goal, something that describes the rate of change of soil moisture as in time with the inputs and the outputs that we can see that are connected to the hydrologic cycle: rainfall, canopy interception, runoff, evapotranspiration, and percolation. Now, of course, this is an equation that is not valid at a point, but is averaged over the routing zone, over the what we call ZR, the active soil depth, basically the O and A horizon put together, where most of the roots are. Hydrologists also call it the active soil layer because it's really where the action of hydrology takes place. So how is this equation related to the Richards equation? Well, it's, as I said, it's related to it by an operation of averaging vertically over ZR. So we start from the equation here. This is just what we saw, and then we average integrate basically between Z at the surface 0 and Z at the bottom of this layer ZR, and see what happens to all the terms. And here it's what happens. So we take an integration. The first term and ZR are considered constant, so they go out of the integral. And then we can, of course, the spatial integration, the vertical integration gets into the time component here and can be done inside the derivative. So we can actually define a vertically averaged soil moisture equation S bar like this. So it's the integral between 0 and ZR of the local at a point relative soil moisture divided averaged over ZR. We call this S bar, and this gets into the first part of the equation. This is what we have on the left-hand side. On the right-hand side, when we integrate the advection part, we get, there is a derivative, so we get the flux at the surface and the flux at the lower level ZR. So this is simply Ks times 1 that comes from the gravitational component, and here is the gradient of the metric potential at the surface and at the bottom ZR, plus the negative contribution of the integration of the whole sink term. So this is the overall uptake that plants do over the rooting zone ZR. So this is related obviously to evapotranspiration, to transpiration, the uptake of water by plants. And this is a flux at the bottom. If it is pointing downward, it is the leakage, the percolation. We call this capital Phi just to call it water uptake by plant. It's not yet technically transpiration because it's just water that goes from the root, from the soil into the roots, but not yet evaporated into the atmosphere, which will happen later on. We'll see how. And this at the surface, if it is pointing downward, it is basically the infiltration. It's the water that comes from the surface into the soil when it rains. Whereas if it happens to be negative and it's water exiting from the surface of the soil as a flux, it's probably bare soil evaporation, some evaporation directly from the soil. This also can change sign, not necessarily has to be pointing downwards. It could be pointing upwards if this gradient is such that water is sucked from deeper layers into the drier upper layers that we are considering the rooting zone. So in this case, it would be capillary rise. Imagine that you have a shallow water table or something like that. This could actually be an input into the equation. So this is the vertically integrated version of the soil balance equation coming from integrating Richard's equation, and we'll see it has the shape, it has the form of the equation that we are looking for. Now, we want to get rid of this bar, not to take it with us all the time, so we just redefine as the vertically averaged soil moisture without the bar. Just we will understand what that means, and there will be no confusion with this S, because we will never use this S unless we really say it. And so we have porosity, rooting depth. This is the rate of change of soil moisture, relative soil moisture in time, inputs due to infiltration by rainfall. Therefore, minus canopy, so it's rainfall minus canopy interception minus runoff, deep percolation, if it goes down to the deeper layers, and plant uptake. So in summary, we have analyzed the first component of the soil-plant-atmosphere continuum, the soil. We have seen the various classification of soil types. We have defined the key variables at the Darcy scale, porosity, volumetric, and relative soil moisture, and so on. And we have seen the two main curves that define the hydraulic behavior of the unsaturated soil, the retention curve, the curve between linking the soil metric potential and the volumetric water content, and the unsaturated hydraulic conductivity, how fast, that tells us how fast the water moves through the soil as a function of soil moisture. And we've seen the effect of organic matter and plants on them, and we have written the balance equation of soil moisture, Richard's equation, valid at a point. Then we have averaged it to obtain the vertically averaged soil moisture equation, which is here. I'm going to repeat it even in the summer, since it is so important. That is the rate of change of how much water we have in the rooting zone as a function of the inputs and the output. We will use this later on many times. That's why it's here repeated. There is a chapter, a section in the notes about infiltration. We'll leave it to a later time, just because we want to proceed to the other components so that we get enough material to discuss the projects that we will develop together. So we'll come back to the infiltration. Don't read it for now. Homework. Okay, section 323 and 325 of the notes contain this description of how the retention curve and the soil hydraulic properties can be related to the physics of what's going on inside the pores in terms of capillary forces and in terms of laminar flow through the pores. These are two very simple exercises for you to just familiarize with the main numbers and the main variable of the soil. I would ask you to do 3.1 and 3.8 as problems to, again, practice on the Richards equation and read and comment the references of the notes 3.5 and 3.7.